Let's work through this example where we see that the volume of a cone is given by 1/3 pi r squared h. So in this formula here, the r, big R, is the radius of the top circle there, and the h is just the height of that cone. So we're given that the formula for that cone, if it's downward facing, is given by z equals h minus h over r times the square root of x squared plus y squared. So what we're going to do to start out is we're going to actually derive that formula, sort of see that that does give us this cone that we're looking at. So we can start with our basic cone formula. So we have z equals the square root of x squared plus y squared. And we know that that gives us our upward facing top half of that cone. And we've seen that that's going to be a slope here of 1. Right, so if I think about the slope of my edge, I'm going to get 1, right? Because I can think of this as sort of where x equals 0. So then I get z equals the square root of y squared, which is plus or minus y. So that's just a slope of 1. Now, if instead I want to have that height of h and that base radius of r, then I want this slope to be rise over run. So I want that slope to be h over r. So what I can do is I can just put in that h over r here, and now I'm going to get that nice slope of h over r. So I will be able to get a radius of r when I have a height of h. So that's our first step. Now it's going to be easier for us to do this as a downward facing cone instead of an upward facing cone. So I'm going to take that and put a negative in. So that'll send it down to be an upside down cone instead of a right side up cone. But I'm going to still have that appropriate slope so that when I cut it off at a height of h, I will have a radius of r. And now what I want to do is just move that up h. So I'm going to add h there. This is plus h. Negative h over r, square root of x squared plus y squared plus h. And that is going to move that up by h. So now the part above the xy plane will be that cone of height h and radius r, which is what we wanted. So if we do the integral of the double integral over that base region D of the shape, so I'll put in my formula here, h minus h over r square root of x squared plus y squared dA, that'll give me the volume of the cone. Because we've seen that when you do the double integral of some function, you get the volume under that function, above that region D. So what should my D be? That D should be that circle of radius r in the xy plane. So that should be that intersection with that cone with the xy plane, which is that circle of radius r. So now I see that I have this circular domain. I see that I have my x squared plus y squared. So I should go ahead and set this up in polar coordinates. So I get that the volume of the cone is going to be the double integral of, we'll keep all of our constants in there, h over r. We've seen that x squared plus y squared becomes r squared. And r is always positive, so the square root of r squared is just going to be r. And then we have an extra r from our, it's called the Jacobian, as we'll see, but that's just the r dr d theta. That is the same as our dA. Okay, so now what are my bounds on the r, little r? Well, I want to integrate over this entire circle here. So I want to get all of the different radii in that circle out to big R. So I'll go from 0 to big R. And then I want to go all the way around that circle. So we'll go from 0 to 2 pi. So that we can go all the way around that circle. Okay, so now we can go ahead and integrate this. There aren't any thetas in my expression. So I can just pull out the integral from 0 to 2 pi of 1 d theta, and then separately do that integral from 0 to r of h minus h over r we'll call that little r. And now I got to be careful here. This r, this Jacobian, does have to distribute to both of those pieces. So I'm just going to go ahead and distribute that in. So I have an RH minus an h over big R, r squared, dr. So the first piece becomes 2 pi. The second one I actually have to integrate. So I'm going to get r squared over 2 times that h minus h over r cubed over 3. And that evaluates from r equals 0 to r equals big R. So when I plug everything in, I get 2 pi times big R squared over 2h minus, when I plug in big R, h over r, that just stays the same, big R cubed over 3. Okay, so let's put things together here. I can simplify a little bit. So I'll leave the 2 pi for right now. I notice I have an h. This r over r cubed, that just becomes an r squared. So I'm going to pull out an r squared times, sorry, an r times h squared. Oops, no, that's not what I wanted to do. I'll pull out that h squared. Keep saying the wrong thing. Pull out, oops, oh no, I went back too far. Everything is breaking. What's my common term? R squared times h. So I'm left with 1/2 in the beginning, and then I'm left with 1/3 at the end. 1/2 is 3/6, 1/3 is 2/6, so I'm left with just 1/6. So I get 2 pi times r squared h over 6, which is the same as pi over 3 times r squared h. So that gives me the volume of that cone, which is what we wanted to show. So again, what were the big pieces here, right? We had to show that this really did give us the right formula. That was given to us, but we wanted to actually see that that is the appropriate cone that we wanted for the radius and the height that we had. And then we set this up in polar coordinates because we had that circular domain that came with from the intersection of this cone with the xy plane. And we also saw that we had that x squared plus y squared. So then we went ahead and just set this up in our polar coordinates. We had our r dr d theta, that was the dA, and then we just changed the x squared plus y squared into r squared. There were no thetas in the integral, so we could pull out that theta integral out front. And then we just needed to integrate with respect to little r, keeping everything else constant, and then simplify down. So we got our volume formula in the end.